So in the last example, we rounded to 3 significant figures, and we haven't really talked about what significant figures are, so we're going to discuss that next. In essence, significant figures is attempting to capture how accurate your instruments are when you were making these measurements in the lab. So if you could be very, very precise in the lab, then the number that you find as your data that you actually took should be very, very precise. But if you're not so precise, then your number should not be so precise. So how do we account for that in our calculations? So in essence, if we have an instrument that can be very, very careful and very, very specific about exactly how many numbers we're measuring, then we're going to use that to reflect in our calculation. The greater the number of significant figures, then the greater the certainty of our measurement. We're very, very certain that our number is this precise. We have, 28.03, or should it be 28.0281764953, on and on and on and on. Your calculator gives you all those numbers. How do you know which ones are relevant based on the experiment that you did, is what you're trying to figure out. So we need some rules about how to deal with that. If we're not reading it directly off of our instrument or our ruler or whatever it is we're using to measure, suppose we already have the data in front of us and we just want to know, based on the numbers that you've given, the textbook has given us, how many of those are significant, so that when we do our calculations we can carry on saying, yes, this is how well we truly know and understand this number. Okay, so our rules are as follows. All non-zero digits are significant. Okay, non-zero digits. So 28.03, we have 1, 2, 3 numbers. And in this example, we have 1, 2 numbers that are non-zero. All those are significant because they're non-zero. Next, we have to decide about all the zeros. Which of those zeros actually count and are significant? Well, interior zeros, zeros between non-zero digits, are significant. So we have 408. That zero is in between 2 non-zeros, therefore significant. These 2 zeros are in between non-zero numbers. They are significant. So how many significant figures total? 1 by rule 1, 2 by rule 2, 3 by rule 1, 4 by rule 2, 5 by rule 1. 5 significant digits in this number. And that means we were very precise when we were making that measurement. Okay. How about if we have zeros that come at the beginning of a number, leading zeros, 0.0032 or 0.00006? Well, the rule is that the leading zeros, zeros to the left of the first non-zero digit, are not significant. They're only there to hold place to put our numbers where we want our numbers to be, not to actually count in how significant the value is. So leading zeros, not significant. How many significant figures in this number? 1, 2. 1, 2. These first zeros don't count because they don't by rule 3, and they don't by rule 2 either. How about zeros that come at the end? Notice these 2 numbers have a lot of zeros. At the end of a number, it's a little bit harder for us to determine. So we have some sub-rules that help us figure that out. Trailing zeros after a decimal point are significant. Always significant. So if they come at the end after a decimal point, they're always significant. Well, what if they come before a decimal point, but after a non-zero number, like this 0 here? Well, we consider that one to be significant, always significant. And in this number, 1, 2, 3, 4, 5, 6 significant figures, these 2 zeros count. What if they're trailing before an implied decimal, like this number, 1200? There's no decimal here. If there was a decimal, I would know zeros before a decimal point are always significant. So I would know these 2 are significant by this point. But there's no decimal point there, so I can't really say. The problem is that doesn't tell us enough information to know. So if we can imply that there's a decimal place there, then we can say there are 4 significant figures. There could only be 3, or there may only be 2. We don't have enough information to figure it out. That's why a lot of times we use this scientific notation, which allows us then to know immediately all the numbers listed in any number that's listed in scientific notation is significant. So all of these are significant because they're here and this number is in scientific notation. Okay, this is times 10 to the third. 10 to the third means move this decimal place 3 places to the right. And so I would have the number 1200, but I would know specifically there are 4 significant digits. These zeros truly do count in this example. And notice each one of these numbers gives us 1200, but each of them has a different number of significant figures, because here we only list 2, here 3, and here 4. Some books typically will put a decimal point here if these two are supposed to be significant. That's kind of cumbersome, and our textbook doesn't really use that notation, but you should know about it anyway. Okay, some numbers are free from this idea of how many significant figures are there because they're considered to be exact. They're not something that you measured out, that you can only measure to a certain level of precision. This is a number that you define and consider to be an exact number, and therefore does not affect how many significant figures you're going to have in your calculation. So if we had to multiply or add 2 numbers together, how many significant figures should our answer have? These exact numbers won't affect that at all. So they have an unlimited number of significant figures. In essence, they're irrelevant for you to determine how many significant figures your answer should have. So for instance, if you're counting exact discrete objects, 1, 2, 3, 4, 5 objects, then 5 is how many significant, then 5 is your number, and that's infinitely significant, and there's no point in limiting your answer to 1 significant figure because there was only a 5 there. Or perhaps if it's a defined quantity or it's some other type of number, then you consider it to be infinitely exact. Okay, so if I'm doing a calculation with 2 numbers that have different numbers of significant figures, how many significant figures should my answer have? So if we're using measured quantities, and oftentimes we will be because they came from some experiment, we're going to assume, because chemistry is an experimental science, our result of the addition or the subtraction or the multiplication or the division or any other math operation I want to carry out needs to reflect how accurately I actually know my numbers. I don't need to list 8 numbers from my calculator as my answer because there's no way I actually know it that detailed in essence. So we don't want to lose information we have that is significant, and we don't want to tack on extra numbers saying we truly know something very accurately when we don't. And so we need to know how to deal with these significant figures in all of our calculations. So we have division and multiplication rules for significant figures. So multiplication and division, the result of the answer of your multiplication or your division should have the same number of significant figures as whatever factor had the fewest number of significant figures to begin with. So everything you're multiplying together or you're dividing together has a certain number of significant figures. This one has 1, 2, 3, 4. You had to determine if that 0 is significant or not. It is. So 4 significant figures. This one has 1, 2, 3, 4, 5 significant figures. And this one only has 2. Since this is the smallest number of significant figures, out of this multiplication, my answer can only have 6.7. My answer should only be 6.7 because I only can have 2 significant figures. So even though my calculator may have given me 6.7208, I can only list 6.7 as the answer because I can only have 2 significant figures. The same goes with the division. Notice here this one only has 3, so 3 significant figures is all my answer can have, so I had to take all these numbers and round them to 3 significant figures. Remember, leading zeros are not significant. So 3 significant figures here. And I'm able to deal with then how precise truly should my results be. Well, what if I'm adding and subtracting? So the rules for addition and subtraction are often easily said by just saying that the number of decimal places in my answer needs to be the same as the smallest number of decimal places in one of my factors, or my add-ins, or my subtrahends in this case. So how many decimal numbers after the decimal place? 3, 2, 4. So my answer can only have the one with the smallest, which is 2. So my answer should have 2 numbers after the decimal place. That's how I'm going to decide how many significant figures are there. Now I know that's kind of weird, but that's how the rule works. So notice in this case I have one number after the decimal place, and in this case I have 3. So my answer can only have one number after the decimal place, 5.7. So this is 2 significant figures. This one is 3 significant figures, even though in this case you don't have 3 significant figures. So remember, addition and subtraction is determined only by the decimal places and not by the number with the least significant figures, like in multiplication and division. It's important to get those separate in your mind and correct for writing them down. Now sometimes it becomes necessary when you're doing these to round these numbers. Notice this is 5.679. I'm only allowed to have 2 significant figures, or I should say I'm only allowed to have one decimal place after my my decimal. And so I have to round this number to something accurately reflecting what my answer is. So 679 means I had to round this answer, and since 7 here is greater than 5, that means my 6 needs to be rounded up to the next number. So I got 5.7 instead of 5.6. Now what are the rules for rounding exactly? Well, we round down to the last or leftmost digit dropped is a 4 or less. So had that number have not been a 7 but was a 4 or less instead, we would have kept the number we had, the 6 that was there. We would have kept it. If it was a 5 or greater, we would have rounded it up, which is what we did to a 7. 5.679 rounded up to 5.7 because that number to the right was higher than 5. So we had to go up by the rule. So sometimes we have to round to the number of significant figures we need. In this case, round to 2 significant figures. So if you need to round this to 2, since 7 is greater than 5, we move this 3 to a 4. Since 4 is less than 5, we keep this 3. We don't round it up to a 4, and we don't round it down to a 2. We keep it as a 3. Since this is right on 5, we're going to round this to a 4. And since this is a 4 and not a 5, we're going to round it and keep it at a 3. Okay, if this was a 5 or above, we'd round this number up to 4. But sometimes you can trick yourself and say, but that's a 9, which means this should be a 5, and so a 5 would make this round up to a 4. But no, then you round it twice, and you're only allowed to do that once. Okay. What if you have calculations that involve multiple operations? You have to add and subtract, and you have to multiply. How should you do it, especially if you're involving rounding? So the way that is normally suggested is that you keep more digits than you need, but that you add something to help you remember how many numbers are significant here. So notice we put an underline under this 7 saying this answer, which is this number, can only have 2 decimal places or 2 numbers to the right of the decimal place. This 4 and this 7 are the only significant ones. But I'm going to keep this 9 here so that when I do this multiplication, I'm including all the information I need, and I'm not rounding too early and then therefore messing up my answer. So I kept this extra information. I did the multiplication. The multiplication tells me I can only have 2 numbers in my answer because there's only 2 significant figures in this number. 1, 2, 1, 2. So my answer can only have 2. But I kept this number extra long so I could do the multiplication. I got this number. I rounded it to 2 significant figures, and so I have 19. I had to keep track by underlying which numbers were significant. Now, there is a difference between precision and accuracy when we're talking about these two things. Often we don't use them in the technical sense, and we should be. Accuracy refers to how close you are to an actual number. All right? There's a target. How close are you to the bullseye? That's how accurate you are. Precision determines how well you can repeat your measurements. So if you knew the correct answer was 10, that's your bullseye, and you were measuring 9.99, and then you measured again 9.98, and then you measured again 10.01, and then you measured again 10.00, and you combine those together, those are both accurate and precise. But suppose instead of hitting 10, you were hitting 5.1, 5.2, 5.3. You were way out here somewhere, but your numbers were grouped close together. Then you were not accurate, but you were very precise. So that's a good way to think about it, just as if you were shooting arrows into a bullseye. So if you want, we can go through an example here. We can make a graph, 3 different students who are weighing a lead block with a mass of 10 grams. Student A, student B, and student C. We can then make this into a graph and determine whether they were accurate or precise. So since we know the true value was 10, we can compare all of their numbers to 10. So notice I put the true mass at 10. That's the blue line on each of these three graphs. And we want to know how close to 10 we actually got. How accurate were we? Here, not close enough to 10 to be considered accurate. But here, well, we were shifted down, so not really close enough to 10 to be accurate. But on this trial, we were accurate right on 10. Pretty close to 10, right around 10. So this one is pretty accurate. These two, not so much. Now, how about precise? Were all the numbers close together? Well, here we had some numbers overshooting, some numbers undershooting, so not precise. So this one is inaccurate and imprecise. These numbers are pretty close together. They don't vary so much, so they're very precise, but they're not close to that line, so they're inaccurate, but precise. And then student C is able to do accurate measurements and precise measurements and nail them both. So that kind of gives you another way of looking at it. So there are ways that your numbers can get messed up. We call those ways error. And so there are a couple of types of error I want you to know about. Random error, error that has equal probability of being too high or too low. It doesn't bias your answer one way or the other. It's just kind of what we would call random. Systematic error, errors that tend toward being way too high or way too low. If you're erring on the side of being too low or too high, it was systematically too high or too low. But it didn't jump back and forth. It wasn't a random error. It was a systematic error. It was an error because you didn't hit 10, but it was systematic in that it occurred in all of your measurements. So we can find ways to deal with each of those, and you need to know about them. Now, solving problems in chemistry. Well, most chemistry involves math, and that means we're going to be converting units a lot. So you need to be very familiar with how to convert units. Please work some of those problems. Watch videos about how it's done. See examples about how it's done. Follow along in your textbook. Find problems to work in groups, work with friends, do whatever you need to do to try to get a lot of experience doing this. You'll do much better in chemistry if you work problems, and then work more problems. Okay? In order to convert units, you're going to be using dimensional analysis. So you need to always include your units in your problems, so that way I always know, or your instructor always knows, how much and then of what. That's your unit, tells you what you're talking about. I had 5. 5 what? 5 newtons. Oh, you have a unit there, so now I know we're talking about force. You had 5 newtons of force. You have to have a unit so you can say how much of what. You must always include this in your calculation, otherwise you're not really communicating what you're doing. So a couple of helpful converting factors or conversion factors you'll see in the front of your textbook, but also notice 2.54 centimeters is 1 inch. So that means 2.5 centimeters is equal to 1 inch. I have a ratio, 2.5 centimeters over 1 inch, and I can use it in either order. And it's a true statement. It's telling me about one thing relates to the other thing. So when I'm converting from or to, I'll use them in different ways. See some examples in your book. Sometimes also I'll have, excuse me, I got ahead of myself. If I'm converting from units or to units, I'll be setting my information up different ways. Remember, I want things to cancel, so I can multiply. If this is a unit, maybe this is 2 inches. Then I'm going to convert to centimeters. Then I'm going to have inches on bottom, centimeters on top. And I know 2.54 centimeters is 1 inch, so I write 1 inch on the bottom, so that way I'm dividing by. Bottom is dividing by. So if this one's on the bottom and this one's on the top, I'm multiplying and dividing by the same thing. Those two cancel each other out. And I'm left behind with whatever was on top, whatever was left over. So I converted to centimeters. So that's often how you'll do most of your problems. And we'll look at one example coming up here. Sometimes units will be raised to a power, like we've already seen cubic centimeters. Sometimes we have square centimeters, square inches if we're talking about an area and that kind of thing. How do you deal with that is the real question. Well, remember, if something is raised to a power, it's the same as multiplying that thing by itself that many times. So if it's centimeters squared, that's really centimeters times centimeters. So look at the example here. If I have square centimeters, that's really taking this first number and squaring it and saying centimeters times centimeters. And so in order to find the conversion between square centimeters and inches, notice what I had to do. I had to actually square this number first. So if I'm converting between square centimeters and square inches, it's not the normal 2.54 to 1. Now it's 2.54 squared to 1 squared. 1 squared is just 1, so that one doesn't change. Or if it's cubed, then it's 2.54 cubed over 1 cubed, so that you can get from inches to cubic centimeters, or cubic inches to cubic centimeters, or however it is that you want to convert. So that's the same as saying you got to multiply it by itself 3 times, or 2 times in the case of the slide here. Okay, so here's an example. Convert 30 milliliters to quarts. You know 1 milliliter is 0.001 liter, and that was by using prefixes, which you're already familiar with. So you know milli as a prefix means 1,000th of whatever the unit is, liters in this case, so 1,000th of a liter. And you know, you probably had to look it up. I don't expect you to memorize this. 1 liter is 1.057 quarts. So using that information, convert 30 milliliters to quarts. So you're given 30 milliliters to begin with, and you want to find the volume in quarts. You know all these conversion factors to relate one to another. We're going to convert milliliters to liters to quarts because we know how liters relates to quarts. So I'm going to take 30 milliliters. That's the number. I just write it down, the one I'm given. Now I'm going to try to convert that to liters. I know how milliliters on the bottom relates to liters on the top. Milliliters on bottom to liters on top. I put milliliters on the bottom on purpose so it would cancel with this milliliter here. So these two go away and I'm left with liters. But I don't want liters, I want quarts, and I know how liters relates to quarts, so I put liters on bottom and those two cancel, and I'm left with how many quarts that I have. I could go different ways. Remember, these ratios can be written top and bottom either way, on top or on bottom. You need them too so that they'll cancel and give you the units that you want. Milliliters cancels liters, milliliters, liters cancels liters, and I'm left with quarts, but I need to make sure that I am working the right way. So my units seem to be correct here because this number seems to make sense because I know a milliliter is a lot less than an actual quart. So if I only had 30 milliliters, already a small number, that should be an even smaller number of quarts because quarts are larger. So we're just kind of trying to check it in our head. Okay, I think we're going to leave it at that for now. This ends Chapter 1. When we come back, we'll be looking at Chapter 2. Thanks for following along with me. Try to work some problems if you can, and it was great having you.